Today we're going to take a look at independent and dependent events. And two events are independent when the occurrence of one event does not affect the occurrence of the other. Two events are dependent when the occurrence of one event does affect the occurrence of the other. If your events are independent events, then the probability for both events to occur is a product of the probabilities of your events. Now, as you take a look at these things, one thing that's going to be noticeable is if your problem is an independent event, okay, when it's independent, okay, your denominators will be the same. Okay. When your problem is dependent, okay, the denominators in your probability are going to be different. Okay, and that's the big key. Okay, so if you want to determine whether something is an independent or dependent event, find a probability of each event happening. If the denominators are the same, then your probabilities are independent. Okay, the events are independent, and if the denominator changes, your probabilities are dependent. A student taking a quiz randomly guesses the answers to 4 true or false questions. Using the sample space below, determine whether guessing 1 correctly and guessing 2 correctly are independent events. Okay. As we take a look at this problem, you take a look at question 1, and then you take a look at question 2. Okay, so the first question, okay, the probability of getting your first question correct. Okay, there are 16 different possibilities up here on the board. Okay, how many of them give you the first number correct? Okay, 1, 2, 3, 4, 5, 6, 7, 8. So our probability of getting question 1 correct is 8 out of 16. Now, what about getting question 2 correct? Well, we've got it here at 1, 2, 3, 4, 5, 6, 7, 8. So our probability there is 8 out of 16. Okay, that tells us that our answer is, this is an example of an independent event. It doesn't matter whether you get the first question correct or whether you get this or not, as to whether or not the second question matters. Now let's take a look at our next piece. A group of 4 students includes 1 boy and 3 girls. The teacher randomly selects one of the students to be a speaker and a different student to be the recorder. Use a sample space to determine whether randomly selecting a girl first and randomly selecting a girl second are independent events. Now, when we start out, we take a look at our probability. Okay, how many students do we have in our group? Okay, there's a group of 4. So we have 4 students in our group. How many of them are girls? Okay, 3. So that tells me that I've got a 3 out of 4 chance of selecting a girl first. Now, can my person be both a speaker and a recorder? The answer to that is no. So if I pick a girl out first, how many girls do we have left for the second event? Okay, there are 2. How many total students do we have left with their names in the hat? Okay, 3. Are those 2 numbers the same? Okay, they're not. So that tells us that those events are dependent, because our probability will change based upon whether the first person chosen is a boy or a girl. Okay, 2 events are dependent when the occurrence of one event does affect the occurrence of the other. The probability of event B given occurs at given point part A has already occurred is the conditional probability of B given A and is written using that formula there. So the probability when working with dependent events is found by taking the probability of the first and multiplying it by the second. Okay, so you're multiplying your probabilities together whether it's independent or dependent events. In the information we just worked through, we said that our probability of picking a girl first was 3 out of 4, and the probability of picking a girl second also was 2 out of 3. Having both people be girls, the probability is 3/4 for the first and 2/3 for the second. We multiply those together, our probability of getting both members to be girls are 6 out of 12, or 1/2. Now, as we go through the probability unit, one thing I will tell you is give me the probability, and I will take the answer either reduced or non-reduced as far as the fraction goes. Okay, so you can either simplify the fraction or leave it as it originally is. As part of a board game, you need to spin a spinner, which is divided into equal parts. Find a probability that you get a 5 on your first spin and a number greater than 3 on your second. Okay, so let's go ahead and say that it's 10 equal parts. What is the probability that we would get a 5 on our first spin? Okay, there's 1, 5 out of 10. How many numbers do we have greater than 3? Okay, well, don't count threes. You've got 4, 5, 6, 7, 8, 9, and 10. So that gives us 7 possibilities. We still have the 10 spots in the spinner because just because I got a 5 doesn't mean that that 5 vanishes off our spinner number. So we're going to multiply our probabilities, and when you multiply fractions, you're multiplying straight across. So 1 times 7 is 7, 10 times 10 is 10. So our probability of getting a 5 and then a number greater than 3 is 7 out of 100. Any questions on that? Okay, a bag contains $21 bills and 5 $100 bills. You randomly draw a bill from the bag, set it aside, and then randomly draw another bill from the bag. Find the probability that both events A and B occur. Okay, that the first bill that we draw is 100. So how many bills do we have total in a bag? Well, you have $21 bills and 5 $100 bills. So that's a total of 25. How many of them are $100 bills? Okay, 5. Now, if you take a look at the information in our problem, one of the big key pieces that we've got here with this is the fact that we've drawn a bill from the bag, and then we set it aside. So now when we take a look at our probability, one thing that you need to be aware of is the fact that our bag no longer contains 25 bills because one of them is sitting on the side, so it now has 24. And the one that we drew was a $100 bill first. So that means there are now only 4 $100 bills in the bag at this time. Our events are dependent events because we laid the $100 bill aside. Had we put it back in, it would become an independent event. So we want to find our probability. Okay, so our probability originally is, on our first try, 5 out of 25 times 4 out of 24. So 5 times 4 is 20. And then when we take 25 times 24, we end up with a probability, or a divisor, of 600. So we have a 20 out of 600 chance, okay, which is 2 out of 60, which would simplify down to 1 over 30. Now, what happens if we return the $100 bill that we draw the first time back into the bag? Well, we said our probability was 5 out of 25. That's not changing on our first draw. But if we put the $100 bill back in, how many $100 bills are there in the bag now? There's still 5. How many are in the bag total? Okay, 25. So we're going to multiply again. 5 times 5 is 25. And then 25 times 25 is 625. Even though our denominator is greater, okay, 25 out of 625 actually will simplify down to 1 out of 25. So there's a 1 out of 25 chance that both of those will happen. Are there any questions on that? Okay, so the probability is going to be higher upon a dependent event, or the chance of something happening will actually be lower on a dependent event than on an independent event. You randomly select 3 cards from a standard deck of playing cards. What is the probability that all 3 cards are hearts when you A, replace each card before selecting the next card, and B, when you do not replace each card before selecting the next card? Now, I'm going to come back to this slide here in just a second, but there are some things that you need to know. There are 52 cards in a deck. Okay, there are 2 red suits of 13 cards each. Okay, and those 2 red suits are hearts and diamonds. Okay, 2 black suits. Of 13 cards each. Okay, the 2 black suits are clubs and spades. There's 1 ace per suit. Okay, there are 3 face cards per suit. Okay, and there are a jack, the queen, and a king. Okay, there are 9 numbered cards per suit, and those numbers are 2 through 10. So as we go through the cards, these are the things that you need to be aware of. Okay, there are 2 red suits of 13 cards each, hearts and diamonds, 2 black suits of 13 cards each, clubs and spades, which means there are 52 total cards, not including the jokers. There are 2 jokers per deck of cards. There's 1 ace per suit, 3 face cards per suit, jacks, queens, and kings, and 9 numbered cards per suit, the numbers 2, 3, 4, 5, 6, 7, 8, 9, and 10. All right, so let's go back to our problem. We wanted to select randomly select 3 cards from the deck of playing cards. What is the probability that all 3 cards are hearts when you replace each card before selecting the next card? We know that there are 52 cards in a deck. 13 of the cards will be hearts. Now, if I put the card back in, how many hearts do I have back in the deck? I still have 13 out of 52. And if I put the card back in again, I still have 13 hearts in out of 52. When I multiply these numbers straight across, this is going to give me my independent probability. And 13 to the third is 2,197 different ways that this could happen out of a grand total of 140,608. Okay, different possibilities where that could happen when we're taking a look at the problem from the standpoint of an independent event. This simplifies down fraction-wise to a 1 out of 64 chance. Now, let's go back to our other set. We start still with a 13 out of 52 chance. But if I lay that heart aside, how many hearts do I now have left on my deck? Okay, I have 12. And how many cards are in that deck now? 51. Now, if I've laid the first 2 hearts aside, how many hearts do we have left in the deck? We have 11 out of a grand total of 50 cards that are in our deck. So now we're going to multiply those numbers together. When we take 13 times 12 times 11, that is going to give us 1,716 different ways that that could happen. Out of a grand total this time, because the cards keep being laid aside, of 132,600 different ways. Now, again, I will take that answer, or you could go ahead and simplify that fraction down. And when we do that fraction, that comes up to 11 chances out of 850. Either answer here that I just circled in red is fine for the non-replace. This is the one for the replace. Okay, so either way can work. Okay, whether it's non-reduced or reduced. Any questions on that? Okay, so let's take a look at another set. This time we're randomly selecting 3 cards, and this time we want to find a probability that none of the cards are hearts. All right, so again, we're going to do part A, where we replace. Okay, so this time there are how many cards that are not hearts? Well, there are 13 hearts in the deck, so that means that there are 39 that are not. Because I'm replacing the card each time, we know that 39 out of 52 is going to be our probability the whole way across. So when I take 39 to the third power, that gives us 59,319. And I'm going to take 52 to the third power. And that's 140,608. That will simplify down to 27 out of 64. Okay, when we don't replace. Or when we do replace. Part B is the not replace. So again, our probability still stays the same to start. But this time the card that I lay down is no longer a heart. We're just going to lay it on the side. And instead now it becomes a 38 chance out of 51 because we laid 1 card out. And now I've got a second card laid out. So that means that our probability now is a 37 out of 50. That we pull out a card that's not a heart. So I'm going to take those numbers and I'm going to multiply those together. Okay, and that gives me 54,834 possibilities out of 132,600. Okay, so we're going to simplify those numbers. And when we simplify, we find out that we have a 703 out of 1760 chance. Okay, any questions or no's? Okay. The quality control inspector checks for defective parts. The table below shows the results of the inspector's work. We want to find the probability that a defective part passes and the probability that a non-defective part fails. All right, so if we take a look here, how many defective parts pass? We're going to do part A first. Okay, there are 3 defective parts that pass. How many total defective parts do we have in this picture? Okay, well, 3 times plus 36 is 39. So 3 out of 39 is a 1 out of 13 chance for a defective part to pass. Any questions on that? Okay, now for part B, we want to find a probability that a non-defective part fails. Okay, so we take a look, we see 11 non-defective parts fail out of our non-defective parts total, which is 461. And that does not simplify. Are there any questions or no's? Okay, the last piece from today is a conditional probability. And when you're working to find probabilities and are given probabilities for both the first and second event, you can find the probability of both conditions by following the formula of the probability of event A and B over top the probability of A. So when we take a look at this problem, this sounds a lot more difficult than it truly is. At a school, 60% of the students buy a school lunch. Only 10% of the students buy lunch and a dessert. What is the probability of a student who buys lunch also buys dessert? Well, what you want to look at is this very first piece. How many buy the school lunch? That is your denominator. Okay, so there's a 60% chance that happens. Now, how many actually buy both? Well, this time we know that there's only 10% who buy both. Okay, so the probability is 10 out of 60, which would simplify down to 1/6. So the probability that a student who buys lunch also buys dessert is 1 out of 6. Any questions on that? Okay, here's another example. It's going to work along the same ways. At a coffee shop, 80% of the customers order coffee. Only 15% of customers order coffee and a bagel. So what's the probability that a customer who orders coffee orders a bagel? Well, there's 80% of the people who actually buy the coffee first. Out of that, 15% of the total customers buy the bagel. So what's the probability that the customer who orders coffee also gets the bagel? Well, what we're going to do again is we're going to take that 15 out of 80 and we're going to simplify that down. And that probability comes out to 3 out of 16. So for every 16 people who buys a coffee, 3 will also buy a bagel. Okay, at this point, we'll go ahead and stop the presentation and take a look at the homework, which is the worksheet for section 12.2.